So my background is in philosophy and evolutionary game theory, very broadly. So a lot of the there's going to be evolution categories here, but evolution of psychological categories is going to be psychology light. A lot of the models I'm going to look at are going to look, there seem to you guys pretty simplistic and maybe too simplistic to really be explanatory in terms of our psychological categories, and that's probably right. But the idea is to provide a sort of basic framework for looking at these things in terms of their evolutionary properties, either cultural or biological property, however you want to think of them. And then maybe we can talk about that a bit in the discussion in terms of the whatever you guys are interested in. Okay, so the target of the talk is what I call moral signals. And the idea is that classifying individuals or individual actions as either good or bad is an essential feature of human moral systems. It's sort of one of our fundamental psychological categories, right? That's good or bad. Now, I think of moral signals in a very, very primitive sense here. So don't take, the term sounds a little bit loaded. Maybe the target is something very rich, as the term suggests. But since there's been very little work in formal modeling here, I'm going to start out as simple as possible and work with a very primitive notion. And the primitive notion is up here. It's that a moral signal is just any signal that both carries information about a particular individual or an individual's actions and sort of recommends or produces reactions from other individuals toward that individual. And that's all I mean. Now, we all know that sort of the moral connotation usually means there's sort of psychological judgment going on here, value judgments. That part is going to be just not in the models. And there are, I'm looking for suggestions for ways that might be added in, but it's oftentimes a very tricky thing to do. So we're going to start with a very basic framework. We're going to use the tools of evolutionary game theory to investigate this. One suggestion made by William Harms and Brian Skirms, who's a member of the Logic and Philosophy of Science department here and a joint appointment in economics and IBS, is to investigate, is to use the context of indirect reciprocity, which I'll explain in a little bit, to see if that provides a setting in which we can get something like moral signals in the sense I just defined to evolve there. Okay, so first I'll say a little bit about reciprocity very generally. We're all familiar with direct reciprocity. The idea is just, if you scratch my back, I'll scratch yours. This is widespread in human behavior, and it's also widespread in many primates' behavior and some less cognitively sophisticated animals as well. Up here I show some macaques and a picture of a vampire bat, which has been known to exhibit reciprocal behavior in terms of regurgitating blood for feeding companions. So there are some very primitive biological examples of reciprocity. Indirect reciprocity, on the other hand, there are several varieties. I'm going to focus on what's sometimes called downstream indirect reciprocity. And the idea is if you scratch my back, then someone else is going to scratch your back, right? So the idea is sort of a community form of reciprocity rather than directly of an individual sort. I think this picture is particularly revealing for the notion I'm talking about. Okay, so in the evolutionary context, we're going to use a little game theory. We'll use the prisoner's dilemma to represent sort of the basic structure of an altruistic interaction. A lot of you are probably familiar with the prisoner's dilemma. The idea here is that the socially optimal solution is cooperate. If we can both cooperate with each other, and if that could somehow be enforced, we would much prefer that. But if you're cooperating, I'd be better off not cooperating, right? Taking advantage of your good behavior and defecting. But if we both defect, we don't do very well. So the idea here is we see a lot of cooperative behavior in nature, and how can we explain it? Reciprocity is one way to explain it. So the question then turns to how can we explain the evolution of cooperation by reciprocity? This is just one way of explaining cooperation in the prisoner's dilemma, evolutionary context. So direct reciprocity, the idea, or maybe I'll say something a little bit more first. The sort of heart of getting reciprocity to be stable in evolutionary systems and getting it to evolve is to have some way of tracking the bad guys, right? Tracking the guys that are defecting so that you can figure out how to defect on them and help the guys that aren't defecting, right? Direct reciprocity, this is easy because you just have a history of play with the same person, right? You just, what did he do to me yesterday, right? I'm gonna, do the same thing today. That's the tit for tat strategy, right? If he was good to me today, I'll be good to him tomorrow. The idea was investigated in detail initially in 1971 by Trivers, and Axelrod and Hamilton have their famous computer simulations that everybody knows about, where they talk about how great tit for tat is in terms of reciprocity settings. The indirect reciprocity setting is a little bit more complicated. The ideas came up in Alexander in 1987, and Kandori investigated the ways in which community enforcement could help stabilize norms and things like this in 92. And that's the sort of setting that we're going to be interested in here, because there's no real need to communicate about others in direct reciprocity. You're interacting with the other guy. In indirect reciprocity, since there's a sort of community involved, the idea is that communication might play an important role in sort of stabilizing these norms, and that's where the sort of idea of moral signals might come up. So the outline for the talk is I'm going to start with a very simple model of the evolution of indirect reciprocity, which was offered up by Novak and Sigman in two papers in 1998, one in Journal of Theoretical Biology, the other in Nature. And then I'm going to introduce signaling into the basic setting, right? They assume that there's an easy way to track reciprocity, easy way to track reputation, and suggest that language might be the way to do it. I'll say a little bit more about that as we go on. I'm going to introduce signaling into this basic setting, and then I'm going to look at the prospects of co-evolving the indirect reciprocity and the evolution of moral signals via the suggestion of William Harms and Brian Skirms. And then we're going to look at some extensions to the model, because it turns out the prospects are not very good. We're going to look at extensions to the model that make them look a little bit better.
Question, clarification.
Yeah.
So in the context of your talk, moral signals are signals that are relevant to questions of cooperation versus defense.
Yeah. And you'll see, you'll be very explicit about what role this is playing in the model. So that's the sort of focus. Okay, so here's a simple model of how indirect reciprocity can arise. This is due to Novak and Sigman in 98, and they have another paper in 2005, which is sort of a survey paper on the various extensions of this model. You have a large randomly mixing population of individuals, and they're going to play a series of games of altruism against other individuals in the population. You never play the same individual twice, so there's no possibility of direct reciprocity here. This goes on for a fixed number of rounds. Each player has a binary image score, either good, bad, in this case 0 or 1, right? And in the simple setting, there are only 3 strategies. There's always cooperate, always be good to everybody, right? Always defect, always never give help to anyone else. Or a discriminating strategy, which looks at the image of their player, right? The image score of their player. If it's a good image score, they cooperate with them. If it's a bad image score, they defect on them. And the image score just comes from their previous action, right? If you defected, you get a bad image. If you cooperated, you get a good image. They allow evolution to occur according to the replicator dynamic. Replicator dynamic is a very broad dynamic which can describe a lot of different circumstances. It could describe cultural evolution, it could describe biological evolution. If we want to talk about that in the question period, I'd be happy to. But the idea just is to look at the change in the frequencies of the strategies within the population, and that's the sort of evolution that we're examining. And one nice thing is, if we imagine that individuals are sort of programmed to do one thing or another, and they change this either by imitation or by inheritance, and then differential reproduction, we can graph this on a nice triangle here. So this simplex represents, every point on this simplex represents a distribution of strategies in the population. So the point right in the middle would represent an equal population of discriminate, defect, and cooperate. If you're close to the top, that's largely discriminate. The arrows and lines here represent the replicator dynamics in terms of where the population is going to move. So let me explain what's going on here. Along the right edge there, there's no movement, right? Because everybody's cooperative, so everybody's all getting the same payoff, and everybody's got a good image score, right? So the dynamics don't do anything there. But if you're along the bottom, you have the standard dynamics for the prisoner's dilemma, since since defectors always do a little bit better than cooperators in a cooperative, in any population of those two, defectors take over. Defectors versus discriminator, however, there's an unstable point here, and if you're above it, discriminators take over. If you're below it, defectors take over. So if you have enough discriminators in the population, defectors can get killed off. Now, cooperators can coexist nicely with discriminators. There are a couple of points that sort of tend to weigh if you have a little bit defectors here, but they go back and get stuck in the edge. There's a transition point in the middle there where things don't move at all. But
what about near the surface? Because I can't believe that the edge is an attractor.
which edge there?
Is the right edge an attractor?
So up here, it's neutrally stable. So so the points just go in there and stick there. They don't move around. So it's an attractor. So all of this ends up at some point along the edge. So any point there is going to stay there.
It's a non-generic situation.
What's that? Yeah.
It's a non-generic.
That's right. That's right. If you add a little bit of if you change the payoffs between these two, it's going to move around a little bit. That's one of the concerns that people have with this particular model of indirect reciprocity is depending on how you change the situation, maybe there's a cost to discriminating or something like this, or maybe there are errors in the population. Things can get destabilized depending on the sorts of errors and costs you introduce, and that's one of the possible problems with image scoring strategies. So I'm glad you asked that question. Yes.
Out of those three, if you provide payoffs, where is that most effective?
Sorry, what's that?
Out of those three, discrimination, cooperation, and defect, you provide a payoff. Where is it more effective?
I'm not sure I understand the question.
I'll wait till the end.
Okay. So some of the possible, I mean, there's a sense in which the discriminating strategy is somewhat paradoxical because if I'm defecting on others with bad image, I'm in a sense going to lose my own good image. So why would I be interested in doing that if there are other discriminators in the population? This has sort of led the discussion on this topic into the notion of standing strategies, which are sort of second-order strategies. They don't only incorporate. So if you're looking at an interaction between two individuals, what reputation should we give a particular individual when he defects? It's going to depend on the image of the guy he's defecting on. If he defects on a bad guy, that's good. If he defects on a good guy, that's bad, right? So this is a second-order strategy. You have to consider both parties and think a little bit on a higher level. The idea was first introduced, as far as I know, by Sugden in '86, but there have been a series of models after that, and largely they're very successful in terms of stabilizing cooperation by indirect reciprocity. However, the models get immensely complicated because once you can start considering all possible second-order strategies, you have thousands and thousands and thousands of strategies, and it's difficult to even tell what's going on in these models. There are also some empirical studies that might give us pause with the move to standing strategies. So this one here, Malinsky, Simon, Baker, and Krambeck in 2001 did some empirical results trying to see if people used something like image scoring strategies or something like standing strategies in actual experimental context. It looks like the results were more in line with people using something like image scoring strategies rather than standing strategies. So you might be somewhat hesitant to run down the standing strategy line if you're interested in explaining the human population, although of course the experimental results are always a little bit messy. So I mentioned this just to sort of point in the direction that the discussion has gone. I'm going to go back to the simple case and put aside worries of Don's because it provides such a very nice simple setting. And since we're going to add a significant complication by allowing agents to communicate to one another using these moral signals, I want to start off in the simplest possible case before we start considering further complications. So we're going to go back to the basic image scoring model and use that as our framework. Now I mentioned earlier that the basic idea behind the image score is that it tracks the agent's past actions, but the actual mechanism behind the image score was never specified in the model. It was just sort of stipulated that it was really good at tracking agents' past action. When they're pressed on this point, right, or when they consider this point, Novak and Sigmund suggest that human language is going to be the thing that allows you to track image, because you can only do so much by direct observation.
Image, you do mean reputation.
What's that?
Image is reputation.
Yeah, that's right. I'm using the terms sort of. Image is reputation. Reputation is image in these models. If you go to the standing strategy, reputation takes a little bit different form. So when I say reputation for the time being, just think of image. So the here's a nice quote. The overriding idea relevant to human societies is that information about another player does not require direct interaction, but can be obtained indirectly either by observing a player or by talking to others. The evolution of human language as means of such information transfer has certainly helped the emergence of cooperation based on indirect reciprocity. Here are a couple of other choice quotes, one from Novak and Sigmund and one from a philosopher, Kim Sterelny, 2003, sort of echoing the same sort of sentiments, only in the other direction. Not only might language be important for the evolution of indirect reciprocity, but the evolution of indirect reciprocity might be important for the evolution of language. And so you can see that last line of the Sterelny quote, language is superbly adapted for social monitoring. Now, there have been some models that have sort of looked at both the evolution of communication and indirect reciprocity at the same time. This Nakamura and Kawata model is one of them. They have a paper called The Evolution of Rumors That Discriminate Lying Defectors or something like that. It's a pretty interesting model, but it's more complicated than where I want to go right away in some ways and too simple in other ways. They think one thing that if you allow agents to sort of start and spread rumors about other agents and about themselves, the thing that's going to be problematic for the evolution of cooperation by indirect reciprocity is lying defectors, guys that lie about their own image and about the image of others. So how can you get rid of these guys? And they have very complicated, rates of spreading of rumors and things like this. The model I want to look at is going to involve just very simple communication, right? So two guys interact, and then they get one of them is allowed to send a signal to the next guy who interacts with, and just one-step signals. And we're going to allow every possible strategy you can imagine with that simple setup. They restrict themselves to a certain subset of strategies, and I think they miss a very dangerous one for the evolution of cooperation. Okay, so how am I going to incorporate the basic, a very simple signaling system into the models of indirect reciprocity? This is a Lewis sender-receiver game from David Lewis in 1969. His dissertation called Convention. It's been extensively studied in the Logic and Philosophy of Science department by Brian Skirms in particular. It represents sort of the basic case for cooperative communication, the most simple setting you can imagine. Nature flips a coin, choosing between two states. The state of the world is A, or the state of the world is B. The first player can send a message 1 or message 2, and then the second player has to choose an action, little a or little b. Little a is best for big A, in state big A. Little b is best in state big B. Both the sender and the receiver want the right act to be performed in the right state. So they have to figure out how to communicate between them. If you let evolution in the replicator dynamics operate in this simple game with probabilities 1/2 for A and 1/2 for B, you get convergence to a signaling system every time. So it's a very nice result. You get efficient communication pretty easily out of this simple game. So maybe we can do something like this in terms of the evolution of moral signals, but in terms of, instead of the state, instead of nature choosing the state is what the guy do to me, right? It's either the guy's a good guy or a bad guy, right? And I want him to be punished or not. So you send a signal to the next guy who interacts with him. Here's the model. We want, as before, members of a large randomly mixing population. We're going to have them play a series of one-shot Prisoner's Dilemma games. their strategy is an ordered pair of functions, right? So they have their strategy just tells them what to do when they encounter an individual with a certain image, and then what image to give that individual, right? What signal to send about that individual after they've interacted. So they look at what the agent did to them, and then send a signal to their next opponent. And then when you meet an individual, you look at what their image is, or what their previous opponent told you about them, and then act on that. We can represent the strategies as ordered quadruples. It just makes it easier. So CD01 means that means cooperate if opponent has a 0 image, defect if the opponent has a 1 image, send 0 if the opponent plays C, and send 1 otherwise. The images are the sort of complicated nested functions, right? So you look at what's my image at round n? Well, it's going to depend on how I reacted to his previous image and what signal he sends about my reaction, right? So it looks kind of messy when you present it like this, but mathematically it works out pretty nicely to calculate what the images are. Okay. The idea is when each pair meets, each responds to the image of their previous opponent and it receives a payoff. Based on the prisoner's dilemma matrix that I gave earlier. Although you can vary those payoffs and get similar results. So the specific payoffs don't matter all that much. After interaction, each opponent gives their new image by sending a signal to the next player. For simplicity, we're going to assume that all players have an initial image of 0. You don't have to have this assumption. You can give them a random image, or you can have a sort of neutral image, a non-zero 1 image. Now, that makes the model significantly more complicated, and not all of those variations make the results robust. But I don't want to get into those complications right now for sake of time. Now, if we're interested in that, I can talk about that later. Here's how you calculate the fitness. I won't go into it, but the fitness just comes from the repeated interactions. You go through the population, play a series of games, and you just sum up the total of the series of games, and you get the total fitness. Evolution occurs according to the replicator dynamic. You compare the fitness with fitness of a particular strategy against the average fitness in the population. If it's higher, your frequency goes up. Of course, this is bounded at 1. Okay. So we want a benchmark case because we want to sort of judge the effects of introducing moral signals into this setting of indirect reciprocity. Does it make it harder? Does it make it easier? Is it possible for these guys to go evolve? So we want a benchmark case. And the benchmark case is going to be this model's analog to Novak and Sigmund's case, right? Which is just this. If we just restrict ourselves to these 3 strategies, we get a simplex that looks very, very similar to Novak and Sigmund's. So the evolution behaves exactly the same, and we have a nice setting to compare ourselves. It turns out that the number we're going to be keeping track of is 79% of the time we end up in some sort of cooperative state, right? Now we haven't included the other possible signaling strategies, so we don't know about what happens with moral signals in this case. This is just assuming everybody speaks the same language and it's working nicely. Right? So that's our benchmark case. We'll expect things to decrease. The question is how severely. Okay, so here are the simulation results. We just ran these 1,000 times, and there are various combinations, so I'll go through these. The first line is the benchmark case. The second line is what happens if you allow agents that invert the meaning of the signals that are being sent, right? So agents that think 0 means bad guy and 1 means good guy, right? It turns out that none of those guys survive in any resulting populations, right? Because they cooperate with defectors. It's a bad thing to do. And they defect on cooperators, which is a good thing, but all the cooperators die out in most cases. But it turns out none of these guys survive in any of the resulting cases, but they severely hamper the evolution of indirect reciprocity. Okay, there's another way to deviate, right? What happens if I screw up the meaning of the signals, right? So let's suppose it's just the defector that's doing that, right? Because the defector wants to screw up the meaning of the signals. This is sort of the worry of the previous model I talked about, right? It turns out that guy hampers it too, but actually not so bad. And he does eventually get killed off in 52% of the cases, and you wind up in a cooperative state. So it's actually not as bad as it was initially thought. But what happens when we include all the strategies? It's disastrous. Almost no cases result in cooperative equilibria, And the one that do result are inefficient, which means there's some defection going on in those cases, and communication is not very good. This less than 1% result means the coevolution of indirect reciprocity and moral signals in this basic model just isn't very plausible. You can sort of get a feel for why it's so bad by looking at a particular subset. And here, it's just like the benchmark case, except instead of the cooperator obeying the sort of standard linguistic conventions, the cooperator sends the bad signal for everybody. This is the guy I call the two-faced cooperator. And if you look at just that guy, he completely eliminates. Just that face, he completely eliminates any hope for the coevolution of indirect reciprocity.
So this is someone who cooperates, but then bad.
Cooperate, yeah, he's a two-faced cooperator. He cooperates with everybody he meets. He's a nice guy, but always says bad things, right? Yeah, there are some people, yeah. Yeah, to give you a sense of what's going on here, here's the simplex where, so this is our standard discriminator. This is our defector who actually uses the language in sort of the normal way in accordance with this guy, right? But it's and then here's the two-faced cooperator, right? Well, what happens is a two-faced cooperator, this line is no longer neutrally stable, and he can invade the discriminators and eventually pave the way for defection. How does he invade? Because look, these guys are all cooperative. Well, not exactly. Since this guy, suppose we're all up here and everybody's a discriminator except for one two-faced cooperator. The one two-faced cooperator says bad things about everyone, right? So these these discriminators start defecting on each other, right? But these guys never say anything bad about that one guy, right? And so he always has a good image, right? So he invades by screwing up the reputation tracking, right? Not by defecting on anyone. He's not a bad guy. He just invades by screwing up the reputation tracking.
So the reason he's so
You can't say
effective
don't
in doing
believe what
this,
he says.
What's that?
exactly. The reason he's so effective is that you don't have another level which tracks his verbal.
His language, yeah.
Yeah.
I'm gonna get to that. That's one of the things I introduce. So that's exactly right. We need to add pressure on the signaling strategies, right? If you want this to work, there are two ways to do it. You can add an exogenous benefit, where individuals receive a bonus to just signaling correctly. So we just stipulate that using the signals in this way is the correct way. Maybe that conforms to some other outside linguistic convention that they have an interest in keeping up, right? Maybe that's what's going on. Or maybe they confuse the game they're playing, right? Maybe they confuse this game of indirect reciprocity with a different common interest signaling game, right? Like the Lewis sender-receiver games that we have really good results with that. So there are two different ways you can sort of suggest that there are exogenous benefits to these cooperators, or to using the signals properly. And by using signals correctly, I just mean in accordance with the rest of the population, right? In particular, whatever the dominant proportion of discriminators is. There are also endogenous ways, which is exactly what you suggested, right? Adding another level, right? So the idea is to incorporate it into the very same system, allow them to somehow talk about each other's talking, right? And so I'm going to look at both of these extensions here. So if we think about just there's some outside standard outside of the setting of indirect reciprocity that's the right way to use language, and they get sort of a bonus for this. Just participating in the linguistic community makes them feel good or gives them some sort of fitness bonus because there's other benefits. And so we're just going to give them a bonus of a payoff here, and that's just X. And that's when you use 0 for cooperators and 1 for defectors. That's your bonus, right? If you do that, you get a bonus payoff. And it turns out that, yeah, you can start stabilizing cooperation if you do this. And you get rid of inefficient equilibria. All of the equilibria are efficient. Everybody's cooperating all the time, and everybody's using the sort of appropriate signals to maintain it. But you need a pretty substantial bonus before you get up anywhere near the 79%. In fact, you never quite get up there even with really substantial bonus. Now notice, so, I forgot to mention, this was on the slide, I forgot to mention verbally, they're only playing 5 rounds of this game. If you cooperate every round, of this game, you're only going to get a payoff of 50, right? If everybody cooperates every round of this game, so a payoff of 15, just stipulated, is very substantial, right? This is a one-time bonus of 15, so they don't get this every round, but they get this just once. But it's pretty substantial relative to the payoffs for the indirect reciprocity and their diminishing returns. But it works, and you get efficient social systems. Okay, what if we have sort of an entangled signaling game, right? If they can't distinguish between a common interest signaling game, like I showed earlier, the Lewis sender receiver game, and the game that they're actually playing, and that sometimes they're playing that common interest that game, we'll say just one time per generation, and give them a bonus of Y for it. So this is just explaining what's going on. There are two states of the world, A and B, that occur with equal probability. One player observes this and sends signal 1 or 0. This is exactly the game that you saw before. The other player acts accordingly, but rather than little a and little b, it's going to be C and D because it corresponds to the actions in the game because they can't distinguish between the two. We'll say that C is best in state A and they get a payoff Y, and B is best in state D and they get another payoff Y. And we'll say A and B occur with equal probability. What happens in this case? Well, this case it turns out to be very interesting. There are two types of cooperative populations that can evolve, and they evolve if you have a substantial payoff to that other common interest signaling game. They can evolve a large percentage of the time, so it works quite well. The interesting thing here is there are two different types of cooperative populations that evolve. There are populations that are all these discriminators that all use 0 for cooperators and 1 for defectors. But there are these other guys that use 1 for defectors and 0 for cooperators, right? So they've inversed the meaning of the signals. These are polymorphic mixes because since everybody starts with 0 as it was stipulated, they need a bunch of cooperators to sort of get cooperation off the ground, right? So this population here, the CD01s, these standard discriminators are sort of the innocent until proven guilty guys, right? That's one moral system that can evolve. The other guys down here, these DC10, are the guilty until proven innocent guys, right? I'm not going to cooperate with you until I hear something good. And if you have a substantial number of these guys in the population, you can get cooperation off the ground. Although it's not completely efficient, it's pretty good, right? Yeah, there are some initial rounds of defection because these guys don't trust anyone initially, but then once people start cooperating, then things get spread around. And it turns out this works pretty well. You can sort of view this as these are two different moral systems that could evolve, right? So there's sort of a conventionality here that comes along with allowing moral signals to co-evolve with the indirect reciprocity. You get conventional moral systems as well. Okay. What about the endogenous way, which I think is the most interesting way? So how are we going to do that? What we're going to do is we're going to add a probability Q suppose A and B interact with each other, right? Normally, A would just send the signal to B's next opponent, say D, right? And that's all the information D would get. But instead, we're going to have, with a small probability Q, in the simulations that I'll present here is 10%. 10% of the time, the interaction between A and B is observed by C, as well as the signal that A sends D, right? And C says, hey, wait. Did A say what I would have said about that, or did A say something else? If A says what I would have said, I'm gonna send a signal to A's next opponent, right? That calls A a cooperator, right? He's signaling in the right way, right? And if he sends a signal different than me, I'm gonna send a signal that calls him a defector. So I'm gonna intercept.
When you say different than me, you mean assuming that I would tell the truth.
Right.
No, there's no real truth in this system until you've reached a stable state. Right? Because
I thought he observed the.
Right. So he observes an interaction, right? And he knows what he would say, what signal he would send about a particular individual's action, right?
You mean whether he knows what he was, and he knows whether he would lie or tell the truth.
There's no line in telling the truth yet, right? It's just a signal with no meaning attached to it. There's no meaning attached to it until you've reached an equilibrium. So for instance here. Right.
You don't know the meaning of yes and no. You just know you'd say yes and he'd say yes, and so you're both saying yes.
Yeah, you're just saying 1 and 0, right? So if we go back to the previous case, maybe this will help clarify things. There are two stable populations. There's a stable population of all of these guys. In this case, one turns out to mean the guy defected, right? 0 means the guy cooperated. But in these other cases, 1 means the guy cooperated, right? And 0 means the guy defected, right? So it's
So it's the evolution of the meaning of
yeah,
this.
it's the evolution of the meaning of these terms. We didn't bake in good and bad here. We just had 1 and 0, right? What turns out to happen is once these populations stabilize, in some of these settings, they fixate on a meaning. They figure out how to classify individuals as good or bad. That's what's going on. Does that make sense?
So they're not learning a meaning, they're evolving a meaning.
That's
Yeah.
correct.
Yeah. Well, it depends on how you interpret the dynamics. But yeah.
So one thing I'm not clear on is whether the signal that the observer is going to send says, I saw something wrong.
What's that?
Is the observer going to send a signal that says, I saw something which is a mismatch between verbally presented reality and actual reality?
Okay. So all he's doing. So
That was the question I was.
oh, okay.
trying to
So let me put it this way: the strategies only have 2 components, right? They're what to do with a particular imaged player, right? Right. And that's sort of what they take to mean that image to mean, right? And then there's what message to send about when I see a particular action, right?
Think of it in terms of Luke's robots yesterday.
Sure,
He
that
had
would be
the
good.
robots where they were making such utterances of some sort or another, and the other robot had to try to make an interpretation for that sound. And so the same thing with the zeros and ones, except this is done with dynamics rather than with robots.
Well,
So-
more simply put, if this guy says 1 and I would say 1, I say we agree.
That's right. That's
That's
exactly
all there
what's
is
going
to
on.
it.
That's right.
That's it.
It's just
Right.
a matter of saying
So
whether
it's-
we agree or not about what we would say.
So you're not
That's-
really sending the signal, he's a liar.
You're saying
That's right,
we
you're not
agree
sending
or
that
saying we
signal.
agree.
Right. Not yet. It could evolve, right? I mean
Right.
that could right. If a signaling system stabilizes, then in a sense what you're saying is, I mean, that'd be one way to interpret it, but it's not built in. I mean,
But you're only testifying that he said the same.
that's
that
it.
He said the
That's-
same thing. that I
That's
would
right.
say.
Yeah, that's it. That's how you judge.
That
Yeah.
imputes somebody to be a liar under the condition that everybody shares agreement about what they would say.
Sure. Yeah. So yeah. So all you're talking about is whether or not they agree.
That signal is agreeable.
Not right away.
Only
No,
once.
eventually.
It's the same.
What's that?
Yeah.
Yeah.
It's the same as agreed upon. Everybody agrees about the meaning of it's the same. That's what-
Yeah. That's right. Okay. So the idea is that I mean, this is exactly what I said. If B's signal matches what C would have sent regarding A, C labels B whatever corresponds to a cooperative action. That's saying we agree, right? He said the same thing I would have said, right? And then otherwise, the other signal. Okay. So what happens in this particular setting? The first thing to note is that it does serve to eliminate these two-faced cooperators, right? It turns out those guys don't survive. The cooperative outcomes that do emerge are a mix between, are always a mix between these guys. Here, everybody is always cooperating with each other. They don't all use the same signaling strategies. But notice, since everybody's always cooperating with each other, they never have to use that second signal, right? And so they never notice that they're disagreeing. Right? Some people would be upset about that in a sense, right? Some of the individuals would send the signal that discriminators would notice as the defector signal, but not everybody would, right? In these cases. So the signals, these systems are pretty are pretty robust when they evolve. So we can say it's possible for an image tracking signaling system to evolve in the context of indirect reciprocity for that same system to be the mechanism for its enforcement. Right. However, that's the good news. The bad news is that if we include all these strategies in the population, how often do we get the cooperative outcome? It's less than 2%. It's like 1.5%.
When you say that they emerged, do you mean that there was no signal? So if you
Yeah.
use very
So the mixed results are, look, it's possible here to get a coevolution of signaling in indirect reciprocity, but it's not likely. Okay, so here are some conclusions, and then maybe we can clear up any confusions that may have arisen. So the coevolution of signaling in indirect reciprocity is far from straightforward. You have to think about how these pressures from are getting placed on the signals and things like that. The big story is you're going to need some sort of way to police the use of signals, otherwise you're going to destabilize cooperation. We can include an endogenous benefit to signaling, which makes it possible to co-evolve indirect reciprocity in a signaling system, which will serve as a basic reputation tracking mechanism. However, if we don't have some external benefit to signaling property, it doesn't look like that's very likely. When we do include such external benefits, it looks like we can involve different moral systems that use the signals differently, right? So there's a sense in which there's a conventionality about the moral signals and moral systems, corresponding moral systems that arise in those settings. So I'll say another note. This is never intended to be sort of a sweeping, largely explain everything about moral signals. The idea is to pick a very simple starting point and see what we can get from that. And I think we can get some interesting results from that. And these were those. So that's what I got.
So if I'm understanding correctly, the signals are point to point. You just tell one other person.
That's right. That's right.
Have you examined? Gossip is often sort of broadcast.
Right. So
seems like that could change things.
yeah, there are many ways you could do this, right? You could say I could send a signal that gets that hits many people, right?
Or percolates to
or we can send chains of signals or things like this. I haven't looked at any of those in particular because it makes the model very, very complicated, and all of a sudden it's very difficult to start examining like the whole space of possible strategies. But I think it's ripe, right? I think it's ready. Like I think given this basic framework, we can start thinking of these simple extensions, right? If we can investigate them in nice ways, maybe we can get some interesting results and sort of see if we can combine different extensions. I haven't looked at anything like that, but I bet you could get some pretty cool stuff.
It's kind of the eBay model, right?
Yeah.
Sort of where people are able to just sort of endorse or not endorse.
Yeah. So there are, one way to think about it is that you could imagine, so this is just binary, right? It's 1, 0, but you could imagine a whole range of possible scores where you sort of, when you interact with somebody, you talk to a whole bunch of people, right, about them, and you get a sort of aggregate, right? And then you could have threshold strategies and stuff like this, and that would be one way to integrate a lot of information into a particular interaction, into a particular signal.
I'm not sure if you can answer this question, but if you were to take a community, a large community,
Yeah.
and their intention is to become larger, right? And they were to choose between discriminators, cooperators, and defectors, who do you think they would value more?
Discriminators. Because discriminators do two functions, right? First of all, they're very cooperative, right? So they help out the overall, they help out everybody because they're cooperative. But cooperators do that too. Why would you prefer discriminators to cooperators? You prefer discriminators because they also serve as the policers, right? And it's good to have those guys around. That way, if any defectors arise, discriminators will help take them out. Does that make sense?
Yes, it does.
Okay. I'm not sure I answered your confusion earlier on.
Well, I think that's probably because it's a confusion. Just let it sit.
Oh, sorry.
Over there.
Oh, sorry.
I was just wondering if this kind of thinking has been applied to empirical types of situations like Survivor, TV show or something. Take data from there for
That'd be great.
Player A.
So, I do know of some studies done in anthropology which look at the role of gossip in community enforcement, right? So they look at the sorts of conversations. They try to track the way in which language is really tracking the behavior of individuals, right? So sit around the campfire or whatever and tell you stories about how much of a jerk that guy is and things like that. I don't know of anything that's been done in nice controlled experimental context. Although I would be delighted if somebody could point me in the direction of something that has been done. And I think once you have, there are a whole range of models, especially when you get into the standing strategy things, once you have a specific model in mind, it seems to me that it suggests certain empirical studies you could do, and if you had the data, you might be able to put some of these models to the test in the right circumstances. But I think it's all pretty young. A lot of these models were just put on the table in the last 8 years. So I don't know of a lot of the empirical studies other than what sort of things do matter for whether or not I cooperate. Is it standing strategies? Is it image scoring strategies? There have been some empirical results there, but in terms of the bigger picture, I don't know much. Kimberly?
I wonder if we could revisit Paul's confusion a little
Yeah.
bit, because I don't think it's uncommon confusion in these games, and
Yeah, I don't
it
think so
actually
either.
bears on our algorithm as well, because we often get the same confusion. So one thing I want to just point out, which may help or may not, and you can help me along as we go, is that in these situations, it is true that they're learning the meaning of the categories as they go along, right? So it's not like language learning in the sense of learning an established grammar. Okay, so that is one important distinction, I think, in these moral categories as well as in the color category evolutionary game theory approaches, and that there's no meaning that's set upon until you get these stable solutions.
Yeah.
So can you just expand on that?
Yeah, I think the best way to get that sense is to
Yeah.
go back to the basic sender-receiver game rather than trying to talk about it in the context of the moral signals. If we just go back to the basic sender and receiver game, there are two equilibria here. Maybe I can draw them on two stable equilibria in terms of the signaling system, right? So there's state A, state B, message 1, message 2, A, B, right? And so player 1 has to decide how to map the states to the signals, to the messages, right? And one way to do that is this, right? And then player 2 has to decide how to map the messages to the actions, right? And if they both map like this, then they're both getting the payoff, and the messages are tracking the state of the world in a very nice way. But if the whole population works like this, right, and somebody comes along and tries to do this, right, tries to map like that, they'll call him. There's a sense in which he's lying, right? But he's only lying in a population that has a language like this, right? That tracks the signals like this. Because if he's in a population where the other guys do the same thing, right, and the receivers do the corresponding strategies, the dotted lines represent another possible way of the signals tracking the world.
Well, in your second order thing, the endogenous case, what is exactly the new signal that's being sent?
In the endogenous case. Okay, so in that case, what happens is, so I observe an interaction between Don and Lewis, right?
Okay.
And I see that Don cooperates and Lewis defects, okay?
Okay.
You are going to play with Lewis next, right?
Uh-huh.
And I see the signal that Don sends you, right? So I observe the interaction. I see the signal that Don sends you.
Uh-huh.
I can look at, well, wait a minute. Did Don say what I would have said about Lewis's action?
Now, when you say what I would have said,
Right.
that means what I would have said about Lewis's action if I was telling the truth?
No, it's what I'm pre-programmed to say about
Oh,
Lewis's, right?
what-
Because
Why
here the
would
strategies
you-
are just.
Why would you have that rather, since you know what?
Who needs all that extra garbage about whether I'm telling the truth? It's just a matter of sending the signal saying I agree with.
And
I
the
would
thing
have
is,
said the
in a
same
well-mixed
thing.
population, there might not be a truth. That is the other thing, right?
You saw this, I don't understand
Oh.
what you're sounding.
It's because I can't just say Lewis defected, right? I have to use a signal, right? I have to send either 1 or 0. I can't say Lewis defected. I have to say 0 or 1,
Okay.
and then you have to interpret 0 or 1. Does that?
Oh, I got it. I'm sorry.
Okay.
I should have got that.
Can you answer this question? What's the best way to prevent community from making a judgment over whether something is good or bad?
Oh, to prevent a community entirely
Yeah.
from making any such judgments?
Yeah.
Best way to present that. So having a value-free community.
Get rid of bad guys.
I'm not sure I can give a detailed answer to that question.
Yeah.
One way to do it, right, is if the population, I mean, maybe they're in a social setting where they're not playing games like The Prisoner's Dilemma, right, and they've no need to enforce cooperation because cooperation might be self-enforcing, right? If they're playing a game like the Stag Hunt or a coordination game where cooperation is self-enforcing, right, where it's just a bad idea to deviate. In that case, you'll have no need to talk about. You'll have no need to transmit these values, right?
Yeah.
Because anyone who deviates is going to do worse off and is either going to die out or decide that they don't want to do that anymore,
Yeah.
right? So I guess here's one thing I can say: you can change the game they're playing, right? And if they're playing a different game, then you won't need these sort of value judgments.
Yeah.
Does that make sense?
Could you give show the last slide with the simplex?
The last slide.
Yeah, that one. We had one word right there.
This one. Yeah, this is a crazy simplex.
Yeah.
This is one you helped me figure out the interior of.
Yeah, and what happens then is rather everything is going to that point in the center. On the upper part of the basin is that point, it looks like.
Which one?
Where you see, you have that spiral there.
Oh, so the spiral. So this is going out.
Oh, it's going out.
Yeah.
So
So there's
I
an
thought it was going in.
Yeah, so there's an unstable equilibrium
Yeah,
right
okay,
there.
fine.
This is a saddle point here, and so
Yeah.
is this. This is a saddle point going in,
Okay.
and this is a
I
saddle point
just looked at the. Okay.
Okay. Yeah, so this is a unstable equilibrium. And so the guys that start around here, they go through this big, sort of spiral, but all end up down there. Right? Everybody ends up.